Good afternoon. So we are going to start our session. Atul, can you hear me?
Yes, ma'am.
Okay, you can speak loudly.
Yes, ma'am.
So this is week 4 sensor and actuator problem solving session. I am ARPITA Biswas. This is about me. I am ARPITA Biswas. I'm a student of PhD in electrical engineering from Indian Institute of Technology, Jodhpur, and I did my MTech from IIIT Jabalpur in micro nanoelectronics. I did my BTech from WBUT, Kolkata, in electronics and communication engineering. And this is more details about me. And the class schedule is every Tuesday 7 to 9 p.m. So in this session we are going to discuss some question, and if you have any doubt then you can directly ask me.
Okay, ma'am.
So we are coming to our first question. Which of the following statement is true or are true for a biosensor? Now comes to the first option, that biosensor convert a biological signal into electrical signal. And the second option is biosensor are used to determine the concentration of substances and other parameters of the biological interest, even where they do not utilize a biological system directly. So the first option is both A and B, second option is only A, and the third option is only B, and the fourth option is none of the above. So please unmute yourself and try to give the answer.
No, I think only A.
Only A. It means biosensor convert a biological signal into electrical signal.
Electrical signal.
Okay. Why not B?
I don't know properly, but I'm thinking only A is.
Do you know what is sensor? Atul,
Yes,
what is a sensor? Actually, sensor is a
sensors are
device.
saying that sense something and
Hello?
convert into electrical signal.
Hello? Yes?
Sensor is an instrument that sense something and convert into electrical signal.
Yes. Sensor is a device which transfer any physical signal into a electrical or a mechanical signal. So now comes to the question, what is a biosensor? Please unmute yourself. What you are understanding from this word biosensor? Am I audible?
Yes, ma'am.
Okay. So what is a biosensor? In biosensor, some biological signal convert into some other signal like electrical, mechanical, or on any physical or optical signal, right? So what is happening in the biosensor? It's convert biological signal into some electrical signal. So first option is right. And what they are saying in the second option? Biosensors are used to determine the concentration of the substances and the other parameters biological interest, even where they do not utilize a biological system directly. It means this sensor is determining the concentration of the substance. whatever the substance or whatever the biological biomolecule they are taking, it depends on that concentration and the others parameters. Like if we are taking if we are vary the parameters or the concentration of the biomolecules, then it can we can get the response in that way. It means when we are increasing or decreasing the concentration, the response also, the output also changes. And biological biosensors are used to determine the concentration of the substances and the other parameter of the biological interest. And also it depends on the other parameters like concentration and the others, like if it is protein, liquid or fat or something is, like if you are taking any gaseous molecules, gaseous biomolecules, then it can depends also it. Okay, so the right option is both A and B. Are you getting my point, Atul?
Yes, ma'am.
Okay, so the right answer is both A and B. It is clear to you?
Yes, ma'am.
Okay. You can try to give the answer whether the answer is right or not. Okay. So we can further discuss
Okay.
on it. Okay.
Okay.
Now coming to the second question. Is 1813 a positive photoresist in spin coated 1/3-inch wafer followed by soft bake using the hot plate? The purpose of this soft bake is, first option is drive away the solvent from the spin resist, and second option is annul the shear stresses introduce the during the spin coating. Third option is the solidify the film, and the fourth option is the all of the above. So coming to the first question, that what do you mean by the positive photoresist or the negative photoresist? Do you have any idea, Atul?
No, ma'am.
Okay. So positive photoresist is whenever this
Actually, I didn't take any class.
sorry, your voice is not clear. Hello. Atul?
Hello. Yes, ma'am. Actually, मैंने एक class ली. I didn't take any class of this session.
Okay, no issue. But now you can clear your doubt, na? Whatever question I am putting here, you can ask if you have any query, but I can explain you.
Okay, ma'am.
Okay. So coming to the first question, that what is positive photoresist, and first we will discuss why the photoresist is needed. So when we go for the photolithography technique, what do you mean by photolithography? It is a pattern transferring process. Like if you are going for the patterning of a like a ID pattern on the substrate, or a heater pattern on the substrate, then what do we do? We go for the photolithography process. And in the photolithography process, what we do, at first we deposit some of the material on the device. Like if we go for the micro heater patterning, then we at first deposit the nichrome, chromium nichrome, and then on the nichrome we have coated some of the photoresist. Like if the photoresist is positive or negative, depending on it, we then we loading the mask, and then we expose the then we UV expose, and depending on the mask pattern, it is coming, the pattern is transferring from the mask to the positive photoresist. Then we go for the developing process. What is the meaning of the developing process? When we dip the wafer after exposure, when we dip the wafer into this developer, then what is happening? If it is positive, listen carefully, if it is a positive photoresist, the covered area means there is a nichrome layer, then or oxide layer, then we are coated a photoresist, then there is some patterning which is coming from the mask. Here is a mask, then the this is mask, then it is the photoresist, then below the photoresist there is a oxide layer. So the mask pattern is transforming from the pattern is transforming from the mask to the photoresist, then it is transforming from the photoresist to the oxide layer. So when we are using the positive photoresist, what is happening, the covered area, when we develop the dip the wafer into the developer solution, then the covered area is protected and the exposed area it is dissolved into this the exposed portion dissolved into the developer solution. So it is positive photoresist. And what is happening in the negative photoresist? For the negative photoresist, the exposed portion become more harder and the covered portion become more soluble in the developing solution, right? So is 1813 a positive photoresist? What is happening here, the positive photoresist is spin coated 1 3-inch wafer. So in a wafer the positive photoresist is spin coated and then the wafer followed by a soft bake. Then before the when we go for the soft bake process, after the photoresist coating we go for the soft bake process. Because and now the question is coming, the purpose of the soft bake process. Now you can explain what is the purpose of the soft bake. Can you guess what is soft bake process? And no need the actual answer, but what you are getting from the word the soft bake process? Have you heard the word bake, Atul? Hello? Please unmute yourself. I will explain, but at least you can try, na? Atul? So the first option is drive away the solvent from the spin resist, and second option is the annul the shear stresses introducing during the spin coating, and third option is the solidify the film, and the fourth option is the all of the above. So the first option, what it is saying, the drive away the solvent from the spin resist. So what is happening for the soft bake process is it also remove the solvent from the spin resist, and also it annul. It is the temperature of the soft bake is near about 90 degrees centigrade. Hello.
Hello.
Okay, now you can tell the answer. At least you try, then I will explain everything. Have you heard the words bake? So coming to
Yes,
the
ma'am.
question. Okay.
Hello.
Huh.
Soft bake is the physical process of conservation of liquid cast resist into a solid film.
Okay. So when we go for the soft bake process, before before the UV expose and after the photoresist coating, we go for the soft bake process, because we at first we want the drive away the solvent from the spin resist. So we want if there is any solvent is present in the photoresist, so it is drive away. And second thing, annul the shear stresses introduced during the spin coating. and also solidify the film. It is an when we put the photoresist on the wafer, it is in liquid format. So when we go for the soft bake process, it solidifies this film. So the right option is all of the above. Okay.
Yes, ma'am.
Have you any doubt?
No, ma'am.
Okay. Next we are moving toward the question number 3. A 5-inch mask plate having a 5-inch mask plate having dark feature and transparent background. Then the mask is dark field mask, bright field mask, grey field mask, or black and white field mask. So can you guess the answer, Atul? If any mask have the dark feature, it means whatever the pattern we want, it is in dark color and the background is transparent. So what type of mask it is? Atul, do you have any idea about mask? Hello? You are not audible. At least try. Hello? Your voice is not audible. So if the mask plate having dark feature and the transparent background, then it is called the bright field mask, because the only the features we want, it is in dark shade, and the background, the most of the area is in transparent. That's why this type of mask is called the bright field mask. And if the opposite is happening, like if the background is in dark feature and the Atul, hello, can you hear my voice? Hello, Atul, can you hear me? Hello, actually your voice is not coming. So listen, if the mask having the dark feature and the transparent background, whatever pattern we need, it is in dark, and most of the area of the mask is transparent. So that type of mask is called bright field mask, because most of the area of the mask is transparent, and only the feature whatever we want, this is in dark color. That's why this type of mask is called bright field mask. And if opposite is happening, then in that time it is called the dark field mask. It means the most of the area of the mask. Yes, the right option is B. You're right. So now next, coming to the question number 4. Atul, now can you hear me? Hello? Actually, your voice is not coming. Okay. So next, coming to the fourth question. The peristaltic pump is an example of negative displacement pump, positive displacement pump, and reciprocating pump, and the last option is the centrifugal. Okay. So the peristaltic pump is an example of the positive displacement pump. So we are moving towards the question number 5. For PDMS molding, silicon elastomer and curing agent are mixed in the ratio of, first option is 5:1, the second option is 8:1, and the third option is 10:1, and the last option is 2:1. So what is the right answer? At least try. Okay, option C. Any others? Parlapelli? Venkatesh? Please unmute yourself and try to give the answer. For PDMS molding, silicon elastomer and curing agent are mixed in the ratio of,
and exactly, but 8:1 or 10:1.
10:1. Okay. Okay, so the right option is 10:1.
Hey ma'am.
Hello. Are you saying anything? Balapelli?
Ma'am, how 10:1? The answer is
Okay.
1/6.
So the amount of the silicon is elastomer, and what is the amount of the curing agent is taking for when they are preparing the PDMS molding? Can you remember? It is mentioned in the lecture video. How much gram or liquid ml is taken?
No ma'am, no.
Okay, actually it is 5 ml they are taking the silicon elastomer, and 0.5 something is taken the curing agent. That's why 0.5 and this is taking 5. So the ratio is 10:1. right? Hello?
Okay, ma'am.
Hello?
Okay.
Okay.
Understood.
So next we are moving towards the question number 6. Gold and platinum integrated electrodes have a thin layer of chromium or titanium deposited beneath the electrode. Why is this done? The first option is to avoid the gold or platinum from reacting with the oxide below, or the second option is metal like aluminum or platinum have poor adhesion to oxide, thin layer of chromium or titanium improve the adhesion, and to the third option is to reduce the cost of uses of metals like gold or platinum, a thin layer of chromium and titanium is deposited, and the last option is the none of the above. So please unmute yourself and try to give the answer. Atul theory option number A. Okay. Palapilli, what is the right answer? At least try, then I will explain.
Madam, B, ma'am.
Can you explain why option B? At least try.
Ma'am, just to guess it, ma'am. I think class not listen number 10, so just I guess it the option.
Sorry, I am not getting you. Can you repeat?
I was not listened, ma'am, class. Just I guess it the option. Just.
Okay, you are right. So option B is the right option because gold and platinum have poor adhesion to oxide. That's why chromium or titanium is used. The thin layer of like in nanometer range of gold and platinum is used. So that's why sorry, in nanometer chromium and titanium deposited, which improve the adhesion. So next we are moving to our question number 7. What is the resolution of 8-bit ADC working at a reference voltage of 3? So this question is directly taken from the lecture video. So unmute yourself and try to give the answer. Palapilli?
Women and them.
What is the right answer?
What is the right answer? I was not listening, ma'am, class. Just now only I can say this is question.
I am not
If I
getting
listen
you.
to the lecture class, I will answer definitely, but I not listen on that time.
Atul? What is the right answer? Okay, B or C. Boyvavi, what is the right answer?
No idea, ma'am.
Okay. So the right option is B, 11.72 millivolt. And how it is getting? If we are solving the equation 3 by 2 to the power 8, then we are getting this voltage directly, and it is also explained in the video. So right option is option B. Next we are coming towards the question number 8. What is a desiccator used for? The first option is the heating substrate, the second option is the cleaning the substrate, or third option is the disposing the waste, and the fourth option is storing substrate in vacuum. So what is the right answer? What is a desiccator used for?
Ma'am, option D.
Okay, Atul. Heating substrate, no. Parlapelli. What is the right answer?
The right answer.
Option B or D? Parlapelli. Okay, so the right option is storing substrate in vacuum. So the right option is the option D. Next we are coming to the question 9. SU8 is the negative photoresist. Areas of the wafer covered with the SU8 when exposed to UV light, will the exposed area become harden or soften or remaining the same or cannot be determined? So what is happening for the negative photoresist when the area is exposed? So what is the right answer? Please unmute yourself and try to give the answer. Okay. Vaibhavi? Parlapelli? What is the right answer?
What is the right?
Option B, soften.
Why soften? Hello? Okay, so can you explain what is positive photoresist, what is negative photoresist? Then you can get the answer easily. What is happening for the if it is a positive or if it is a negative? Like SU8 is a negative photoresist. If it is a positive photoresist, what is happening? Vaibhavi? At least try, then I will explain.
Ma'am, option A.
Okay, why option A?
Because it is a negative photoresist, so the part that is exposed, it becomes hard, and the unexposed part becomes weak.
And if it is a positive photoresist, then what is happening?
The unexposed will become hard, and the exposed will become weak.
Yeah, good, right. So Parlapelli, you got the answer. So now it is clear to all, or any doubt?
Once explain ma'am, what is your photoresist on this question?
So you want to know about the photoresist? Hello. Hello.
Yeah.
Okay, so if we want to pattern something, like if we want to generate it, if we may fabricate a ID pattern or something else now, then what we do, we go for the photolithography process. And in the photolithography process, the first step is, if we are taking a wafer, a silicon wafer or glass wafer. If it is a glass wafer, then we directly go for the deposit the material, or we go for the photolithography process. But generally what we have done, at first we taken the silicon wafer, then we put it then we deposit a oxide layer. In the oxide layer, if we something pattern transfer a pattern, or we make we want to fabricate a micro heater or something ID pattern for the electrode now. Then what we do, at first we deposit a silicon dioxide or oxide layer on the top of the wafer. Then if in that layer we want to pattern, or we want to make some ID pattern, or some micro heater, then what we do, at first we coat the photoresist. Okay, the photoresist is basically two type. It is positive photoresist or it is negative photoresist. So we coat the silicon oxide layer with the positive. At first we are taking the positive photoresist, or we are taking the photoresist. Then what we have done, then we will go for the soft bake process. And in the soft bake process, what at first the photoresist is that it is in liquid form. So when we put a drop of the photoresist and we spin coat it, then we go for the soft bake process. It is the layer become solidify, liquid to solid transfer, and the solvent is present. If there is a solvent is present in this photoresist, then it is also dissolved. Then what we do, then after the photoresist coating, we go for the, generally if it is a positive photoresist or negative photoresist, then we go for the loading the mask. And what is the main aim of the mask? There in the mask, whatever the pattern we want in our device, this pattern is already this pattern is prepared in this mask. So when the UV light is going through this mask, the pattern transfer from this mask to that like photoresist. So then we go for the UV expose. Then when UV expose is done, the pattern transfer from the mask to the photoresist layer. Then after the UV expose, we go for the development process. What is happening in the development process? There is some chemical is present. Then we dip the wafer our device into this development solution. Then what is happen? If it is a positive photoresist, then what is happening? The covered area, there is a pattern in this mask. Like if we want the ID pattern, interdigited electrode pattern on that mask, or some micro heater pattern, if it is in dark form and the background is transparent, then that type of mask is called bright field mask. And if the pattern we want, this is in transparent and the background is black, then it is called the dark field mask. Then in the type, it is also depends on the type of the mask, and also depends on the whatever the pattern we are getting, this is also depends on the photoresist type. So if it is a positive photoresist, what is happen? The covered area become more hardened, and also the exposed area, it is become soluble, or it will when the you put the wafer, dip the wafer into the developing solution, then if it is a positive photoresist, the exposed area will gone. The exposed area of the positive photoresist will gone, and only there is a remaining portion of the photoresist is present, that is the covered area. Then what is the process after the development process for the positive and negative photoresist? And what is happening for the negative photoresist? For the negative photoresist, if we are using, then the covered area become more soluble. When you dip the wafer into the solution, then covered area will gone, but the exposed portion become more hardened. So what is telling here, AC-weight is a negative photoresist. So what is happening for the negative photoresist? The covered area become more soluble. When you dip the wafer into the solution, the covered area will gone, but the exposed portion, it is become more hardened, so it will remain on the substrate. So now it is clear to you what is happening for the negative photoresist. So the exposed area become more hardened. Now it is clear to you what is photoresist, what is the need of the photoresist. Palepelli? Palepelli? Now it is clear to you?
Okay, madam, understood.
Do you have any doubt? Hello.
No doubt, madam.
Okay, so we are moving towards the next question. So our next question is, a typical photolithography process involves the following process. The first option is the spin coat photoresist, then mask loading and exposure. The third option is the stripping the photoresist, and the fourth option is the etching, and the fifth option is the soft bake process. The sixth is the hard bake process, and the seventh is the developing. So what is the right way to do the photolithography? So the first option is 2 1, then 5 4 6 7 3, and the second option is the 1 5 2 7 6 4 3, and the third option is the 1 2 3 4 5 6 7, and the last option is the 5 1 2 4 7 3 6. So please unmute yourself and try to give the answer. What is the right option? Atul's option C. Okay. Palapeli, what is the right option? I already explained about the photolithography process.
Ma'am, option 2.
Okay. Palapeli? Palapeli Venkatesh, what is the right answer? Am I audible? Balwant, can you explain why option B is the right option? Vaibhavi? Am I audible?
Yes, ma'am.
Okay, can you explain why option B is the right option? At least try, then I will explain.
Ma'am, because option B, it goes according to the process. Like first we spin coat the photoresistor, then we perform soft bake, then it's the mask loading and exposure, then we develop it. Once it's developed, we do hard bake, and then we strip the photoresistor using etching. So option B is the perfect, suits the process. So option B.
Atul? Can you hear me? Please unmute yourself and try to give the answer. Palapeli? Atul? Can you explain why you told the option C is the right answer? Then I will clear your doubt. Atul? Yes, Bhavi, you are right. The right option is the option B, because at first we spin for the photoresist, then we go for the soft bake process, then after that the mask loading and exposure has done, and then after the mask loading and UV expose, we go for the developing process, and after the developing process we go for the hard bake, and after hard bake we go for the option 4, which is the aging process, and after the aging process we go for the stripping the photoresist. Can anyone tell any liquid which is used to stripping the photoresist? Atul? Palapelli? Any of the liquid which is used to strip the photoresist?
No idea, ma'am.
Okay. Have you got the answer why the option B is the right option? Or if you have any doubt, then I will explain again. Palapelli? Have you got the answer?
Yeah, ma'am, yeah.
Okay. Atul? Do you have any doubt? Okay. So, can anyone tell any of the liquid which is used to strip the photoresist?
Ma'am, acetone.
Okay. And the aging process? Any of the aging process? Like which solution is used to aging the silicon wafer? In previous classes also I have explained. So can you tell any of the name of the? Which process we have?
Buffer hydrochloric acid.
No, buffer hydrofluoric acid we have used to age the silicon dioxide. Okay, now I am telling the aging process of the silicon. The silicon aging process, which chemical is used? Have you remembered? Boy baby?
I'm not able to recollect.
Actually, I'm not getting you. What? Boy baby?
I'm not able to recollect, ma'am.
Okay. Atul? Like wet etching process you use to etch the silicon wafer when we go for the pressure to build fabricate the pressure sensor. So in that time, which wet etching process we have done to etch the silicon wafer? Like in the bottom side we etch the silicon to make that type of shape now. That type of shape. So in bottom side, what type of etching process we have done to etch the silicon? Yes, to etch the silicon dioxide, we can use the buffer hydrofluoric acid. But now my question is, what is the chemical we have used, or what is the process we have used to etch the silicon? Palapelli? Atul? At least try now. Have you heard about the TIMA process or KY solution? Any of you?
Yes, ma'am. Yes, ma'am.
So, no, which type of process the TIMA?
Wet etching.
Wet anisotropic or isotropic process?
TEMA is uh, TEMA.
The shape is like that. So what type of process it? That type of. Okay.
I don't know, ma'am.
Can you tell me what is anisotropic or what is isotropic process?
Ma'am, TEMA is anisotropic.
Hmm. Why?
I don't know, ma'am.
Actually, what is happening in the anisotropic, in a particular direction it age out. Okay, like in a particular direction it is age out the silicon or something, but the wafer it is present in a particular direction, it age out the wafer. But what is happening for the isotropic aging? In isotropic aging, it is in all direction, in all of the direction it is age out the wafer or the substrate. But in anisotropic process, in a particular direction it age out. Okay. And it also depends on the plane of the wafer, like in between the 111 and 100 there is a angle between it, what is 54.7 degree. So it age out in a particular direction. In the, that's why the TEMA is a wet and anisotropic process. But for the buffer hydrofluoric acid, you can see it age out in all direction. Okay, that's why it is a isotropic aging. So now we got the answer. Baby?
Yes, ma'am.
Okay. So next we are moving towards the question number 11. After acid spin coater in soft bake process, what is the temperature of hot plate? So in the soft bake
65
process,
degrees.
when we go for the
Yes, ma'am.
hello,
Yes, ma'am.
what is the right answer?
65 degrees.
Okay, and okay. So next question is, after SU8 spin coater in soft bake process, the times depends on the thickness of the SU8, thickness of the oxide, and third option is the thickness of the substrate, and the last option is the all of the above. So what is the right answer?
Thickness of the substrate.
What is the here? What is the substrate is taking? If we are taking silicon wafer and then we put the SU8 or the oxide, after oxide deposition, if we go for the SU8 coated, then is it really depends on the substrate or the thickness of the substrate? Like what is happening for the so-called this positive and negative photoresist when we are coated the wafer with the positive or negative photoresist? What is happening? If you go for the soft bake process, what is the temperature of the soft bake process in that case?
It is 65 degrees. For
Just a
there
minute,
will be
actually your voice
SU8.
is not clear. Just a minute. Now tell me, what is the soft bake temperature for the positive and the negative photoresist when used?
For positive, for negative it is 65 degrees.
No, it is not only the for the negative. For negative and positive photoresist it is different, and is for the SU8 it is different. SU8 behave like a negative photoresist, okay, but it is SU8, and for the positive and negative photoresist it is different. But okay, SU8 behave like a negative photoresist. So what is the soft bake temperature for negative and positive photoresist, and what is the soft bake temperature for SU8? In the both cases it is different.
So, ma'am, for positive photoresist, it is 90 degrees.
Yes, and the time.
But and 1 minute.
Okay, and for the SU8,
For SU, it is 65 degrees, and it depends on the thickness.
thickness of the what? Substrate, oxide or SU8?
All of the above.
No, the right option is the option A, the thickness of the SU8. Because if the thickness of the SU8 is larger, na, in that time it takes more time. And if the thickness of the SU8 is less, then it needs lesser time. Also, it need less than 1 minute. Also, if it is the thickness of the SU8 is very less. Okay.
Okay, ma'am.
Like the thickness of the substrate is very it give very greater than the SU8 or the oxide layer. It is only on the oxide layer, and the thickness of the SU8 na very less, but the thickness of the substrate is very greater than this oxide or the SU8. That's why it does not depends the soft bake process here does not depends on the thickness of the substrate. It depends on the thickness of the SU8 or the thickness of the photoresist, right?
Okay, ma'am.
So we are moving toward the question number 13. In the case of SU8 spin coated after soft bake, which process is used? Loading the mask, hard bake, or UV expose, or PR developer?
Hard bake.
Hard bake. Okay. And why hard bake is done, and why they are not using the mask loading or UV expose? Do you have any idea?
Ma'am, because of the material, like it is negative PR and SU8, so first it is necessary to resist the material, like give strength, stability to the material, and then load mask and mask over it.
Yes. Yes, you are right. So that's why we are after the soft bake process. When they use the SU8, na, then they go for the hard bake process. Now the next question is, in the case of SU8 spin coated in hard bake process, what is the temperature of the hot plate? The first option is 65, second option is the 90, third option is the 120, and the fourth option is 200 degrees centigrade.
90.
And what is the hard bake temperature for positive or negative photoresist?
120.
Yes, and what about the time?
1 minute.
And here, what about the time?
It depends on the thickness of the SU8.
Yes. So we are coming to the question number 15. In the case of SU8 spin coated after hard bake, which process is used? Loading the mask, hard bake, UV expose, or PR developer?
Loading the mask.
Yes. Now coming to the question number 16. In the case of SU8 spin coated after PR development,
Hello, ma'am. You're not audible.
Just a minute. So in the case of AC weight spin coated, after peer development, which process is used? Aging, hard bake, or bake at 125 degrees centigrade, or none of the above? So what is the right answer?
Bake at 125.
Yes. After the peer development. So can you again for AC weight, can you explain the process flow? What is done after what process? Can you explain the total process flow?
So, ma'am, we have a silicon wafer. We first clean the silicon wafer.
Okay.
Once we get a cleaned silicon wafer, then we use the SU8 spin coater. Once the spin coater is done, we perform soft bake, which is at 65 degrees Celsius, and the time depends on the thickness of the SU8 material. One soft bake is done, hard bake is done, which is at 90 degrees, and the time again depends on the thickness of the SU8 material. So once hard bake is also done, like the material is now stable, we load the mask. Once the mask is loaded, we perform UV exposure, and after UV exposure, PR development is done. And once PR development is done, we get the structure, we get the required structure. So we bake it at 125 degrees to give it more stability.
Okay. So next we are moving towards the question number 17. Example of the optical MEMS. First is the optical switches and the digital switches, and the second option is the micro mirror devices. Third option is the bistable mirror, and the fourth option is the laser scanner, and the last option is the all of the above. So example of the optical MEMS are
All of the above.
yes, the right option is all of the above. Because optical switches or the digital switches both are the optical MEMS, and the micro mirror also it, and this question is directly taken from the lecture video. And in the lecture also the sir has explained that the micro mirror devices and the bistable mirror or the laser scanner, all of the above are the optical MEMS. So next we are moving toward the question number 18. Evaluate whether the following statement is true or false. The RF MEMS smaller, cheaper, better way to manipulate the RF signal. So it is true or false?
Maybe true.
Yes, it is true because RF MEMS size is smaller and it is also cheaper and it better way to manipulate the RF signals. So the next question is the question number 19. Three basic steps of the MEMS fabrication is deposition, patterning or etching. Second option is the oxidation, deposition and etching. Third option is the oxidation, patterning or the etching. And the last option is the deposition, patterning or lithography. So what is the right answer? Think and then try to give the answer. What is the main basic steps in MEMS fabrication? Because all of
Ma'am,
these are
option
the
one.
okay option. Can you explain why not the other option is the right option like B or C or D?
Because, ma'am, for deposition, oxidation is used. So if we select deposition, so even oxidation is covered. So that rule out B and C. And for option D, lithography, it is the entire process, that is deposition, patterning, etching is a part of lithography process. So option A.
Okay. Can you tell me a deposition process like the metal deposition process main there is a two deposition process like not offer the only the oxidation. Any other deposition process do you know?
Physical vapor deposition, does
Yes,
this
and
count? Sputtering, what is that?
actually sputtering is a part of the physical vapor deposition. Okay, so there is a two way, like
Okay.
the chemical vapor deposition or the physical vapor
Chemical.
deposition, right? So what is the difference between the physical vapor deposition and the chemical vapor deposition?
Uh, in physical vapor deposition, maybe a beam, like we have to preheat, like it is done using preheat where um, the chemical is heated and it is collected by the wafer holder. And for chemical, maybe chemical is used to perform deposition.
Okay, chemical is used. Then what happened in this chemical? We use the chemical for the chemical vapor. At first, we are coming to the chemical vapor deposition. So for the chemical vapor deposition, we are taking the chemicals. Then what happened?
No idea, ma'am.
So when we go for the chemical vapor deposition, then in that time we heated the chemicals. Okay, there is a furnace. There is a three types, three basic type of CVD is present: atmospheric pressure CVD, or low pressure CVD, or PECVD, plasma enhanced CVD. Okay, or there is also a MOCVD, metal oxide CVD types is present. And in what happened, we are simply taking the example of the atmospheric pressure CVD. What happened in that case, we are taking in the board, we are taking some chemicals, and there is a zone, first zone, second zone, and third zone, so we can vary the temperature. Okay, so whatever the boiling point or the melting point of the chemicals, whatever taken, and also the source means where the chemical is kept now, the melting point of that material is very larger than the chemicals we are taking for the CVD process. So in that time, so what is the melting point of the chemicals? We are set greater than the melting point, so it can vaporize. And we all in the same times we are taking some, because here we are our wafer is present, and here we are taking the chemicals. So at first we heated the chemicals above the melting point of the chemicals, so it can vaporize. Then after that it is reacting. Okay, when if we taking an example of the MOS2, molybdenum disulfide, if we want to deposit the molybdenum disulfide on the wafer, silicon, on this simple silicon wafer or the silicon dioxide wafer. So what we have done in this process, we are taking the MO3, molybdenum oxide, and also the sulfur. Okay, so in the if in the first zone we are taking the sulfur, and the melting point is near about the 200 degrees centigrade, and the MO3 is greater than 650 degrees centigrade. Then what is happen when we increase the temperature above this melting point of this chemical, the both chemicals, then it evaporate and it start to react, and it form the MOS2. Then how this MOS2 vapor here in the third or the second zone we have taken the wafer, how it is deposited, that's why we are taking an carrier gas. So in our cases, most of the cases, we are using the argon gas, which is not reacting with this chemical. Only molybdenum oxide and the sulfur is reacting to each other, and then it's form the MOS2, and we flow the carrier gas argon, and then using this carrier gas, this MOS2 is deposited on the substrate. Now it is clear to you what is happening for the atmospheric pressure CVD.
Yes, ma'am.
Okay. So we are taking the chemical, then we heated the chemical above the melting point of the chemicals, then it start to evaporate and it react with each other and it forms the whatever the molecules we want. It forms in that way. Then we flow the carrier gas, and with this carrier gas, this material whatever present in the vaporization mode, it is deposited on the substrate. But what is happening in the case of PVD? Can you explain?
Ma'am, in PVD, the material it is kept in a heating furnace. When at particular temperature it is set and for particular time, so it is collected on the wafer holder which is on the above, and on after that time we can see the silicon wafer, the deposition happening over there.
How the deposition is happening, like in for the chemical vapor deposition now, some chemical is present when we evaporate, then using the carrier gas, after reacting these molecules it deposited on this substrate. But what is happening for the sputtering, or what is happening for the PVD system? How the material deposit on the substrate? My question is it. Are you getting my point? How in the PVD system, how the material deposited on the substrate?
No
The entire
idea,
process
ma'am.
will clear your all of the doubts, I think.
Yes, ma'am.
Now the CVD process
I
is clear, and all of the lithography process for AC weight and for the negative and positive photoresist, it is also clear to you.
Yes, ma'am.
Yeah, at first
I'll
you
see
try,
the
then I
video
will
lecture
explain
once.
what is happening in the PVD case.
I'll have to see the video lecture once, I think. Otherwise, it would be great if you could explain.
Okay. So what is happening for the PVD? Like if we are taking the example of the sputtering, then there is a there is a wafer holder or wafer is present, but in that case also there is a like target is present. Whatever we want, like if we want to deposit silicon nitride on the top of the wafer, then what is happen? In that case, we are flowing the argon, or here the argon is not used as a carrier gas. Okay, in what is happening for the CVD? For CVD, it is not reacting with the chemicals. It only used as a carrier gas. Okay, that's why the chemical is, after the reacting the chemical, it is deposited on the substrate. But what is happening for the sputtering or PVD cases? The argon gas heated on the target. Like here is the target is present, and the below you see here the target is present, and if we are taking the substrate below, then what is happening? In the target gas, there is a plasma present, and the argon is heated on the target, and some amount of the material whatever we want to deposit now, it like heat, and that material comes here and it deposit on the wafer, like that way. Sputtering, it is physically sputtering, is heated, this argon gas heated, and then some amount of the material whatever present in the target, it is deposited, then it is coming that way, like that way and that way. And in that way, in the below the wafer is present, which is moving, which is rotating, so uniformly this material can deposit it on the substrate. And here target, the target, the argon is heated, like, and that way the some amount of the in nanometer range, or some amount of the molecule, whatever is present in the target is deposited on the substrate uniformly. How it is uniformly deposited? Because we rotating the wafer, so uniformly in all the area it can deposited. Now it is clear?
Yes, ma'am.
Okay. And also there are two types of the sputtering. This is sputtering, RF sputtering, and also they generate the plasma. And also they have to mention the we have to maintain some of the parameters in that case also. But the basic principle is that the argon there is a argon bombarding, like there is a bombarding of the argon ions. Okay, then the argon heated and bombarding, and some small amount of the target is present here, it is deposited. Then here to here the top of the wafer, it is deposited uniformly, and the wafer is rotating. That's why the wafer is rotating, that's why it is uniformly deposited all of the area of the wafer. And can you tell me any except this sputtering process, there is a 2-3 process also present, like PVD. Can you tell me any of the name?
I'm not able to recollect, ma'am.
Okay, like in CVD process, the atmospheric pressure CVD is present. The plasma enhanced PECVD is present. Also, the low pressure CVD is present. That in that way also there is a 2-3 types of PVD, physical vapor deposition process is present, like a thermal evaporation process, and the second is the sputtering. And except this the e-beam evaporation system is also present. So and the same the basic principle of the all of the system are the same. And you also always remember that the source where the substrate where the material is present now, some of the material is present, then we heat it up, then the melting point of the source where the chemical is taken always greater than the chemical is the source of the melting point of the source is greater than the melting point of the chemicals, whatever we want to deposit on the substrate. Okay. Hello.
Yes, ma'am.
So we are moving towards question number 20. Any system that is between dash micrometer is called the MEMS device. The first option is 1 to 100 micrometer. The second option is the 100 to 1000, and then 10,000 to 1 lakh, and the last option is the all of the above. So what is the right answer?
I'm option A. Option
Okay, so the right option is option A. So if the range, the size range in between the 1 to 100 micrometer, then it is called MEMS. So what is the full form of the MEMS?
A. Microelectrical mechanical system.
So we are coming to the question number 21. The MEMS are made up of microelectronics, microsensor, microactuator, microstructure. And the second option is microelectronic, microheater, microactuator, microstructure. And third option is microelectronics, microsensor, microheater, and microstructure. And the fourth option is microelectronics, microsensor, microactuator, and microheater. So what is the right answer?
Option 1.
Can you explain?
Because MEMS, it stands for microelectrical microelectrical mechanical system. So it consists of sensors, actuators. Then it is a system. So it consists of, matlab, it is a system which includes microstructures, small structures, and it contains electronics. So microelectronics. So option
Okay. And what is the brain of the system? If we are talking about the brain, then which one is the right answer? Microelectronics, microsensor, microactuator, or microstructure?
A. Microsensor.
How brain is a microsensor? In your body also there is a sensor is present, like hand. You can sense, no? then where the signal it is going? In our brain. That's in that way also, in the devices, MEMS devices also, at first they sense the data, then it is transforming the brain, then it is replying through the some action. Okay, you can now relate. In our body also there is some sensor is present, like the hand we can touch, the nose we can sense, then where the data is going, our brain, then through the brain, how it is replying through the do some action or the work. In that way the MEMS devices act. Now you can tell me what is the brain of the MEMS devices?
Microstructure.
How microstructure?
I'm not sure because um, otherwise it will be microelectronics.
um, One by one we can you can try to explain that it can be easy to you what is the right answer. Tell me what is happening in the case of the micro sensor or simple sensor, what is happening?
It senses the motion.
Okay.
And actuators, it senses the motion and gives an appropriate action. It performs the action.
What is the meaning it means what is the work of the sensor means, uh, which type of data convert in which form in the
Sensing
sensor?
movement. Uh, so mechanical to electrical?
No, not only the mechanical,
No,
any
not
physical data, any physical data. Like if we are taking that the if we go through a road, then in that road there is a light. So if they sense the human body, then the light is on. So it
so
can
any
detect any
data.
physical data. So it convert into some energy, na? Which type of energy sensor
Electrical
transfer the
energy.
data?
Electrical energy.
Electrical energy, it can be optical or it can be mechanical energy also. Okay, for the sensor. So now what is actuator?
Performing movement, like taking electrical energy and converting it into a mechanical energy.
Okay, mechanical energy means the rotation or do some work. Okay, it
Yeah.
transforming this electrical energy. It means if we are reconnecting it to our body, sensor is taking the data and it gives to our brain. Then what is happening for the micro actuator or actuator? It's taking this data, this electrical data, and it transform into a rotation or some movement, like some work. So here like our nerve, na? So this data is going to this going to the going, and it is doing some work or doing some movement. So micro actuator is the later part, but at first the data the mediator point where the data is going, then using the micro actuator the data is coming out in the form of some doing some movement or doing some work. So then what is happening for the microstructure?
It shows action or it supports action.
No, here they are talking about some structure, na? Some dimension, some structure they are talking about. Right?
No idea, man.
No, actually microstructure, they are talking about some structural which is in micrometer range, like the dimension like 1 to 100 micrometer is present. All of the structure, it is telling about the whole structure of the MEMS devices, how it is look like. Okay. So microsensor is sensing the data. Microactuator, it is convert the electrical signal into some movement or doing some work. And microsensor structure is telling about the structure of the MEMS devices. So except the microelectronics, it is the main part of the MEMS device. It can be called the brain of the MEMS device. So at first from microsensor the data is going to the microelectronics, then through this microelectronics it replies the data, like whatever they are getting the data using the sensor, it doing some it convert this electrical signal or some optical or the some mechanical data into the form of the um, some movement, some work, right? So here the brain of the MEMS device is what is the right answer?
Option 1,
Yes, and the brain is
microelectronics.
microelectronics, right? Which etching process is high etching rate? Wet chemical etching process, dry etching process, DRI, and last option is the all of the above.
Wet etching.
Can you explain the wet etching process? What is happening? What type of etching process is present?
So there are two etching processes, wet and dry. So for wet etching, we get it etched. We use chemicals as TIMA or KOH to perform wet etching. So here we get the wafer can be etched at 54.7 degrees. Whereas for dry etching, the wafer can be etched at 90 degrees. And the wet etching process, it has high etch rate and it has high selectivity, so it is used for removing unwanted stuff, unwanted portion.
And what about the DRI process?
um, it has comparatively low selectivity,
Okay.
and it can be used to for bulk
What is the full form of the DRI process?
deep reactive something with the deep reactive ion etching.
Okay, so in that case, reactive ion etch the wafer. Whatever we want to etch, na, reactive ion etch. And what is
Hmm.
happening for the dry etching? What type of things etch the wafer or the whatever we want to etch?
Sorry.
Like wet chemical etching process, we are taking the chemicals is in which form? Liquid, gaseous, or something else form? Plasma?
For dry etching, it is plasma.
Plasma and also gas. Okay. And for the
Uh,
wet chemical etching process,
TIMA, KOH, or BHF.
so it is present in the liquid form, right?
Yes, ma'am.
Yes. And for the deep reactive ion etching, the reactive ions here etching the substrate or whatever we want to etch. So the right option is the wet chemical etching. Three type of pressure sensors are capacitive, piezoelectric, thermal, or capacitive, electrochemiresistive or thermal, or capacitive, piezoelectric or electrochemical, or all of the above. So what is the right answer? Three types of pressure sensors are.
Option A. Option A.
What is the piezoelectric? Do you know?
Uh, when a piezoelectric is when a thermal energy, when mechanical energy is applied, there's a change in the voltage of the component.
So how it is work or the fabrication process of the piezoelectric pressure sensor? Do you explain? Can you explain the fabrication process of the pressure sensor?
I'm not exactly sure for the process
Hmm?
of fabrication.
Can you try how we can fabricate?
No idea, ma'am.
How it is look like that type of form?
It has a cantilever type structure,
That
if
type
I'm
of
not
form,
wrong.
na? In upper case there is a something is present, and the below case there is h, that type of.
Yeah, so if there's at one end, if it is pressed, so there will be a change in the this thing. So, uh,
There is a diaphragm is present, so we are when we are putting the force on it now, so the some parameter of this material it changes, like if it is electrical piezoelectric type, then the voltage will change. If it is if it is piezo resistive, then the resistance will change of the material, right? So
yes.
how we fabricate this piezoelectric or piezoresistive type pressure sensor? At least try.
We use a concept of doping.
No, we are not. At first, we are taking a wafer. Na? Start from the
Ma'am,
taking a
like
wafer, then clean it. Then what is the process?
we take a wafer, we clean the wafer, then we load mask. Sorry, first there is a coating of piezo resistor. Sorry, PR.
Where we are
Followed
putting
by
a peer. At first, slowly understand the process and then try to explain. At first, we are taking the wafer. Then after wafer, there is a silicon dioxide. Now,
yes, ma'am.
at first think how the piezoelectric, which material, what type of material the change the resistance will change. Wafer is very thick now, it is not going to move, or if we are putting any pressure on it, any force on it. At first what is happened, we have deposited the silicon oxide, the polysilicon. Then we will make the polysilicon the pattern. So what we have done, after the polysilicon both side silicon dioxide, we have coated the wafer with the photoresist. Then what is the process?
Once we have used the photoresist, then we load the mask, bright field or dark
No,
field mask, and
after
then
coated the photoresist, what is the process? You already explained it. Remember, after positive, we are taking the positive photoresist in our case. So after coated the wafer with positive photoresist, what is the next process? Before the mask loading, now there is a small process is present.
okay, doping with the
No, no, no,
material.
no, no. Think, after photoresist coating and before the mask is loaded, there is a small process is present.
Uh, I don't recollect, ma'am.
The soft bake process, no? If we coated the photoresist, then we go for the soft baking process.
We
Any,
go for soft bake after we have loaded the mask. No?
yes, after soft bake process, then we loaded the mask. Then what is the next process?
After loading the mask, we perform we put it under UV light and then we put it under PR developer.
What is happening in the
So,
PR developer if we are taking the positive photoresist?
so the unexposed region becomes weak. So the
Hmm.
unexposed region
And the exposed
etches,
portion?
it becomes hardened.
Exposed portion become hardened for positive photoresist. What is happen for the positive photoresist when it is UV exposed? Then exposed portion for positive photoresist what?
It will stay as it is. No, the part where UV light is exposed, it will be removed,
Hmm.
and the unexposed part will become hardened.
Yes.
Okay, I told Ulta. Sorry.
Okay. Then what is happening?
Then we developed it into a PR.
Okay.
Then
Then
we etch it. Uh,
if there is a silicon dioxide present, then what type of agent we have used?
if silicon dioxide is present, then we use wet etching.
Okay, wet etching, and what is the chemical name?
KOH or TIMA.
No, we are going for the oxide agent, na? TIMA or KOH etch the wafer, the silicon.
Okay, sorry. BHF will be used.
Yes, buffer hydrofluoric acid agent we
Hydrogen
have to use to etch the oxide.
oxide. And then we use acetone to remove the photoresist coating.
Just a minute. After the development, when the pier is removed, then what process we have done? There is a small process.
Hard bake, man.
Yes. Then we go for the hard bake process. And what about the temperature and time?
120 degrees for 1 minute.
Yes. And if we use the AC weight, then what is the temperature?
90 degrees, and
No,
it depends
no.
on.
If after the development we bake the wafer
Achha,
some temperature, na?
125 degrees.
125 or greater than 125. Then
120 degrees. And then we use wet etching, like we use TIMA or QH to remove the SiO2.
but if we go for the at first if we have, then in the back side also now we have to go for the photolithography process, right? It is the front side, and in the back side, here the back side na, so we have to at first do the patterning. How we can etch directly? If we put the wafer, there is also oxide is present on the here the oxide silicon, and below the oxide is present, and here the pattern is here. So in the below side we have to go for another photolithography process. We have to pattern, then we have to etch, right?
Yes, ma'am.
So how we will go? So what is the process flow? Like in the back side there is a oxide present, and how you will now etch the throughout we have to make the cavity. Think and then try to explain. From the back side wafer, then oxide also present, because oxide is in the both side initial stage or wafer, then oxide both side is present. Then we pattern or do the lithography process on the surface of the wafer, on the bottom surface. Now we are going to the bottom side. In the bottom side we have to prepare that type of shape now. So now the silicon is present, and then silicon dioxide present, and how we will go?
So for removing the oxide, we use BHF only, no?
Yes, oxide you can use the BHF, but before if we initially etch out all of the silicon dioxide, na, then when you dip the wafer into the TIMA, then it will etch out all the silicon. But we have to make the that type of shape, like that type of shape, na. So we have to make the we have to transfer the patterning also there, na. So we need the mask. That's why we need again the photolithography process. We need again the photoresist, and also we need the some in the where we want to keep the that type of shape now. There oxide is also present.
Hmm.
So now you think how we will etch that type of cavity, how you will prepare or fabricate. The same process we have to flow. Think and try to give the answer. At first, again we have to coat the wafer with a positive photoresist, and then after positive photoresist coating, what we will do? Again we will follow the same process. Just the pattern is different, and after the silicon dioxide etch now, then we go for the TIMA process.
Okay, ma'am.
And to protect the front side now, we can cover it with the positive photoresist. Throughout the front side we can cover it with coated with the positive photoresist, and back side also we can coat it with the positive photoresist. Then we go through the same process. So now can you explain? I gave you hint.
The process will be same, na, but
Yes, the process is same. You can try, then I will explain where you are doing the mistake. So at least try from the back side.
ma'am, can you only explain?
But
Can you only explain?
at least try, then I will explain. Try na. I gave you hint. At first you coated the wafer back side also you coated with the positive photoresist. Then what after the positive photoresist, what is the process?
Then we perform soft bake.
Yes, after soft
Performing
bake.
soft, we load it with the mask, and then we expose UV light.
Yes,
So once
when we are exposing the UV light now, then the pattern is transforming. Now there is a pattern like the corner side we want, and in between this two now we want to etch out. So the pattern is the same. So we want to keep the photoresist in the side type portion, and we want to etch the middle portion. So the pattern is transforming in that way. So the photoresist in the both side is remaining, and the middle portion, the middle bigger portion will etch out. So the pattern is transforming from that mask to that, and this is the second type of mask. Not the same type of mask. How we get the pattern, the mask is that type. So from the mask the pattern is transforming to the mask to the wafer, the photoresist. So that type, so we want to remaining in that portion, and middle portion we want to etch out. So the mask pattern is transforming now. So after the pattern is transforming, what is the next process? Like UV expose. After UV expose, what is the next process?
After UV expose, we perform the PR development.
Yes.
So now the pattern will be fixed, and
So
then we
when
perform
we are
hard bake.
when we are doing the PR developer, so what is happening in the middle portion now? The PR where it is gone, and only the corner side the PR is remaining. So what is the next process?
So then we'll perform hard bake
Yes, hard
to
bake. Next.
make and once hard bake is performed, then we use BHF.
Yes, when you
Remove
use
the
the
oxide.
BHF now, see when we use the BHF, then the here the photoresist is present, and in middle there is no photoresist. So in middle the oxide is gone. Okay, now there is a only the silicon, only silicon in present in middle, and in two side the silicon and oxide, and also the photoresist is remaining. So what is the next process?
So once that is, we use acetone.
Okay, if we use, now see, if we use the acetone na, then in the both front side and back side we covered with the photoresist to protect the front side. So in that time both side, from the both side the acetone will the photoresist will gone, right? Then what is the
Yes,
next
ma'am.
process?
Uh,
Now
that's it, no,
photoresist
ma'am.
is gone, only the silicon dioxide is present, which is act as a mask. So the
Hmm.
silicon below the silicon dioxide will remain, and in the middle portion when we dip the wafer into the TMA, so we are going to the process etching. So when we are going for the process wet etching, in the middle portion they will etch out the silicon, right?
Yes, ma'am.
Yes. So we will, then it will, yes, so then it will remove the middle portion of the silicon, and we will get the actual pattern, actual the pressure sensor. But you have to maintain that when we are going for the use the buffer hydrofluoric acid to etch the silicon in the bottom side now, in that case your in the front side you have to coat the wafer with the photoresist. But if you are not doing this, when you put the device or wafer into the BHF solution now, in front side we also pattern now, and it is in the silicon dioxide pattern is present, whatever we done earlier now. So if we are not doing the photoresist coating in the front side, in that time we when you dip the wafer in the BHF solution, it etch out the back side HF oxide, and also it can etch the in the front side of the pattern. That's why to protect the front side you have to coat the in the front side with the photoresist. Are you getting?
Yes, ma'am.
Yes. So this is the process flow. So now we are moving towards the question number 24. The benefits of MEMS are: first is speed, second the consumption, third is the size, the fourth is the all of the above, and last option is the none of the above. So what is the right answer?
All of the above.
Yes, the right answer is all of the above. Question number 24. The right way to connect the microfluidic chip with the peristaltic pump is: the inlet of the microfluidic chip should be connected with the outlet of the peristaltic pump, and the second option is the outlet of the microfluidic chip should be connected with the inlet of the peristaltic pump, and the third option is the inlet of the microfluidic chip should be connected with the inlet of the peristaltic pump, and the last option is the both option A and B. So what is the right answer?
Option A and B.
Yes, the right option is A and B, because the inlet of the microfluidic chip is connected with the outlet of the microfluidic peristaltic pump, or the outlet of the microfluidic chip is connected with the inlet of the peristaltic pump.
Yes, ma'am.
Now coming to the question number 26. The peristaltic pump is the closed loop system, the open loop system. Third is the none of the above, and the fourth option is all of the above. So what is the right answer?
Closed loop system.
Closed loop system. Good. Now coming to the question number 27. Peristaltic pump is an example of sensor, actuator, transducer, none of the above or all of the above.
Actuator.
Yes, actuator. But it, because what is happening for the actuator? It transfer the electrical signal or some signals energy into some
Mechanical energy.
action, or it is doing some work, right? So in peristaltic pump also it is doing some work. So it is an example of the actuator. Now coming to the question number 28. In case of peristaltic pump, the liquid is flowing, discrete interval, continuous, both A and B, or none of the above. So what is the right answer?
Discrete interval. Discrete
Yes,
interval.
discrete interval. Can you explain why discrete interval the output is coming or the liquid is flowing?
Because there was one word like it keeps on going on it keeps on going on. I
Actually,
don't
there is a
remember.
system na, like where they are taking the input or the flowing the liquid na. The system is means the structure is like that. Some liquid is flowing, then again some liquid is flowing. So it is not continuous. Okay.
Yes.
So the right option is the discrete interval.
Yes, ma'am.
So next we are coming to the question number 29. For PDMS molding, after silicon elastomer and curing agent are mixed, white desiccator is used. So the first option is remove the air bubbles, and the second option is the remove the dust particle, third option is the cleaning purpose, or fourth remove the humidity. So what is the right answer?
Remove air bubbles.
Yes, remove air bubbles. This is our last question, question number 30. So a 5-inch mask plate having transparent features and dark background. So what type of mask it is? Dark field, bright field, or grey, or black and white both?
Dark field.
Yes, the right option is the dark field. Why it is dark field?
Because in dark field the background is more compared to the transparency.
Oh, okay, good. So here we are ending our session. So our next session in Tuesday 7 to 9. Okay, you can leave.
Okay. Thank you, ma'am.
Thank you.